that will maximize the profit. X being number of units. So what do we need?
Should we just plug in 140?
That's it. In P, yes, in lowercase p. Awesome. So part E, so we have little p equals 280 minus 0.4 times 140, and that's the price per unit. So we have 280 minus 0.4 times 140, and that is the price per unit. So this is 224 per unit. So if we want to maximize our profit, we have to produce 140 units to maximize the profit. For 140 units, we get 14,600, and the price per unit to have a maximum profit is 224. So again, this is an application and a reinforcement of what we studied this in this chapter. What is it all about? I have to have the function. I have to find its derivative. I have to set it equal to 0 and undefined. In this case, no critical number comes from here, but only the one critical number, 140. Putting in the table to know exactly what it gives, because it may be the opposite. I don't know. Maybe I made an error. I cannot assume it's asking me find the maximum profit, but what if I have an error and this does not give me a maximum profit? Once I put it in the table and I study the sign and know for sure that's it. And then I plug it in to find the maximum, and then the final question. Any questions for me? Okay, so let's look at 3.6. In 3.6, we are going to need to look at another application. Of course, they're all applications of derivatives. And we are talking about marginals. And you know what marginals are. Marginal profit, marginal cost, marginal revenue. What are they? P prime, C prime, R prime, and so on and so forth. There may be other functions that we want the marginal to look at, the marginal. By marginal profit, we mean the first derivative of the profit, by marginal costs, and so on and so forth. Then we're going to look at differentials. What is this? We have never discussed differentials before. And the last one is linearization. What is this? I mentioned something, and let me just say here, and maybe we should start with this. It doesn't matter. So if you remember, I tortured you, so to speak, with here's a function, here's a point, and we drew the tangent line at that point. So this is the tangent, and we always wanted to determine the line, the equation of the line. So the equation of the tangent line. And I said a long time ago, why on earth will I care? I have this function at a particular point, any point I want, where the function is differentiable, of course. Why would I even care to find the equation of the tangent line at this point for this? What does this linearization mean? It means at any point on a function where it's differentiable, I can approximate the function here very close to the point by using the line instead of the function itself. And you can say, but who cares about that? It's going to be an error. It's going to have an error in it. Why would I even want to do that? Okay, so here's the answer. So if I have, let's say, f of x equals the cube root of x. So I'm talking about now, so let me write the title, linearization. So I'm starting with linearization. Marginals we discussed. We can go back to them. Of course we will. Linearization is what I would like to talk about, and then we'll talk about differentials. So So this is 1 and 2 and 3, and we start with 3. So let's say I have the cube root of x. And let's say x is, let's say, 8. Something simple, right? The cube root of 8. Now, if you plug in the cube root of 8, what do you get? Anyone?
2.
Good. But what if I ask you, determine the value of this function when x is 7, let's say 7.9. Now this becomes difficult, right? I know that the cube root of 8 is 2, but what about the cube root of 7.9? I have no idea. I have to use a calculator on this. And yes, you can say, but use the calculator and you're done. True. But I want to make a point. So coming back to any function. So if this is a function, and this is a, and of course, this must be f of a on any coordinate system, of course. So this is the function. I pick a point with its x value is a. Of course, the y value is f of a. Can anyone give us the slope of the tangent line at this point? Slope equals slope of this tangent line. I want to determine the equation of the tangent line. Anyone remembers how did we determine the slope of the tangent line at this point, where x is a and of course y is f of a?
Is it f of a divided by a?
No. It's something we learned in calculus. It's calculus. It's not, I don't have 2 points. I cannot write y2 minus y1 over x2 minus x1 because I only have 1 point. So this is from calculus. From algebra, we have this. But from calc, we have this. What is the slope of this tangent line? It has to be tangent. Anyone remembers? What did we say? We used it many times. We determined it, and then we said y minus y1 equals the slope times x minus x1. How did we determine this? With calculus. And having 1 point, just 1 point. We used it many, many times before. How did we determine? Yes?
I was gonna say, if you're looking for just 1 point, should we look for the origin? No.
No.
Okay.
How did we determine this?
The derivative.
F prime of A. Awesome. Thank you. So the slope is the rate of change of the function at when x is a. Awesome. Thank you so much. Who was that, Levi?
Yeah.
So please remember, this is why we know from algebra with 2 points. But from calculus, we learned that the slope of the tangent line is always the value of the derivative at this point when x is a. Okay, perfect. So then, y is f of x, y1 is f of a, f prime of a, x minus a, because x1 is a. So all I did was, in this equation that we know from algebra, I replaced everything step by step. Y is f of x. y1 is f of a. Slope, you gave it to me, f prime of a. X is x. x1 is a. We're going to simplify this. and get f of x, and I will move f of a to the other side. We do not like to say it again.
No, I was just saying, for me, you lagged out for like the last 30 seconds. I'm not sure for everybody else.
Yeah, for me as well.
Okay. Should I say it again?
Yes, please.
Okay, so I replaced y by f of x. I replaced y1 because the point, this is the point, right? The point P is a f of a. So this is x1, y1. x1, y1. F of a, and x1 is a, and x is x. So what I did next, I moved f of a to the other side, and I have f prime of a, x minus a. We don't really like to write f of x here. We write L of x. The linearization of f of x at x equals a. What is it? L of x equals f of a plus f prime of a, x minus a. Again, what does this mean? It means that very close to a, if I use the function to evaluate, or if I use the line to evaluate, the error will be very small. If I want to evaluate here, I have to find another tangent. This is not going to work, it's too far. But if I want to evaluate, like, if this is 8, and I want to evaluate at 7.9, if I use the line, it will be easier for me to evaluate quickly. I will have a minor error, but instead of using the function, which will be more difficult, I will use the line, and I would know that there is a minor error. So let's illustrate with this function that I made up, and then we can choose another example. So in other words, we have f of x equals the cube root of x, and x equals 8 for now. So given this information, find L of x, the linearization at x, or maybe I should write a equals a better. Same thing, at a equals 8. Okay, so all I have to do is find these pieces. So L of x, you already told me that f of a is 2, plus I have to find f prime of x, plug in 2, and then in parentheses x minus 8. But I need to find this piece and put it here. So first let's find f prime of x. Can anyone find f prime of x for us? Remember, it's easier to change this into what before we differentiate it? X to which power?
1/3.
Very good, awesome. So now f prime is 1/3. X to which power? And we have to calculate 1/3 minus 1. Negative?
Will be 2/3.
Very good, awesome. Good, so now f prime of a goes in here. So f prime of 8 equals 1/3 times 8 to negative 2/3. If you have any difficulties calculating this, we can work on with the calculator. Oh, okay, just give me 1 second. 1 second, 1 second, 1 second, because I'm running out of juice here. Let me plug it in. It's plugged in. Okay. Good. So we want 1/3, and then multiplied by 8, and the power, in parentheses, negative 2/3. And here's what we get. And I want to change it into a fraction. And here it is, 1 divided by 12. So this is 1 over 12. And I just put it in, 1 over 12. Okay? Good. So what is the function? So the linearization, which is a linear function that will evaluate this function near 8. If you say, what about a equals 100? No, this function that we just determined cannot evaluate at 100. I need another function near 100. But near 8, I will have 2 plus 1 over 12x minus, and I simplify by 4, minus 2/3. 2 minus 2/3. So then the linearization is 2. I'm sorry, I meant to write 1 over 12 x. So 6 minus 2, so plus 4/3. This, I can use this. Maybe I should put this in writing for you. I can use this L of x to evaluate f of x near 8. But we mean near 8, not at 15. So now, coming back to my question, if I plug in here 7.9, instead of plugging in the function, you will see how close we are. So we had the cube root of 7.9, and the power is 1 divided by 3. Okay, so this is the exact, and this is what we get with the line that we created. 7.9 divided by 12 plus 4 divided by 3. When I click enter, it has to be very close to that number. If it isn't, there is an error somewhere. Here it is. Look how close it is. 4-digit close, decimal digits. So this is the power of calculus. So all I would like you to remember, this was an example. We're going to have simpler examples, but all I would like you to remember is that calculus allows us to approximate a function using the equation of the tangent very close to that particular point. So if we use the actual function, or if we use the tangent, the equation of the tangent at that point, the error is minimal. So if this is 8, you cannot test or determine at 10. It will be too far out. The equation is not valid anymore. So you have to be close to 8. If you're close to 8, left or right, it doesn't matter, but close, evaluating the function or evaluating using the line, the equation of the tangent line, it's not going to make a big difference. So, and I also wanted to copy this number for you here. What was it? So, so this is 1.991666, and the actual f of 7.9 is 1.991631,701. So you can see how close they are. So this is the discussion about the linearization. So let's see if we want to quickly determine another, look at another function. And this is, where is the page number? Yes, 341. 341. Enter. So let's choose another linearization and see how this works. Find the linearization of at this. Is this okay? In other words, we are finding a line to estimate the function. Is 19 okay?
Yes.
Okay, so 19 on 341, and we have f of x equals x squared. Find the linearization, part A, L of x, of f at a equals 3. Good. So what do I have to write first? What is the formula?